Hello everyone. In this video we will continue to examine topic 12.1, the interaction of matter with radiation, and in particular we will introduce quantum mechanics. Alright, so we're going to take a detour here, okay? And a way to understand what we're about to discuss is we're going to discuss sort of the foundations of quantum mechanics. Now, there's a certain amount you need to know about quantum mechanics for the IB. Let's think of those as sort of like principles 1, 3, 5, and 7 of some list, whatever. And what I'm going to do in the next few sections is I'm going to give you a little more than that, okay? And I'm going to do that so that hopefully you can connect 1, 3, 5, and 7 together. That is, you only need to know and be able to respond about and discuss 1, 3, 5, and 7, but having 2, 4, and 6 can help with that. And so I'm going to give you a little bit more than you need to know. And in part, the reason those have been excised is that quantum mechanics is a fundamentally mathematically challenging theory. It's not impossible. It's not crazy beyond you, but it is certainly undergrad level. And so what I'm going to try to do is sort of explain the essence of what you need to connect those ideas. So moving forward, quantum mechanics is a theory founded on postulates, which are like axioms in mathematics. There are a certain number of those postulates, and those postulates are used you combine them, and you can make extremely precise predictions, which are then experimentally supported to an incredible degree. So quantum mechanics is sometimes thought of as our most successful theory, or the foundation of our most successful physical theory ever. And it's precisely because of these predictions that it is so well respected. And it's important to realize that when we introduce it, we're going to talk about the postulates, which do not themselves have independent evidence. So it's not that we have some evidence for these postulates and then take them to be true and see where they go. It's instead, if you take these postulates to be true and combine them, they allow you to make these extremely precise predictions, which then constitute the evidence for the postulates to begin with. And exactly what these postulates mean is not obvious and is debated in a subsection of philosophy known as the philosophy of physics. So we're going to go over some of the postulates of quantum mechanics, some of which you need to know, some of which you do not. The first that we're going to look at is that the state of any system, a system could be a free particle, it could be a couple of particles interacting, or it could be a huge interconnected system. But the state of any system is completely specified by what's called a wave function. Psi of x comma t. It's a function, and given this symbol. And the fundamental property of psi is that the square of the amplitude of psi gives the probability of finding a particle at a position x. So let's start with a whole bunch of these things. The first is psi describes a state. It's a state function. It describes the state of the system right now, and then as it might change, it could describe the state of the system later. Secondly, it is completely specified by the wave function. What this means is it's not an extra thing, it's the only thing. If you know the wave function for a system, you know everything there is to know about the system. That's it. That end game. So psi itself has all the possible information about a system embedded in it. Psi, the wave function, cannot itself be observed, okay? So the wave function is like a field, like the electric field or the gravitational field. And in that sense, okay, some people might interpret psi, they might say, well, it's just a mathematical trick. But if so, it's a pretty convincing one. But in either case, we usually say psi exists, the wave function exists, and it cannot be directly observed, like the electric field or the gravitational field. We can only see what psi means for the particles it describes. We can only see the consequences of the wave function the way that we see the consequences of the electric field or the gravitational field. And then finally, let's talk about this property for a second. This final property is that psi is such, okay, so the defining condition of the wave function is that the square of the amplitude of the wave function gives the probability of finding a particle at position x. In IB notation, this is written like this, which says that the probability of finding a particle at a position x is psi squared dx. And therefore, if you integrate over all of psi squared, you will get the probability of finding it somewhere, which is equal to 1. So this is the normalizing condition, and this just says that psi squared is going to give the probability. We'll talk more about this moving forward. Okay. Fundamentally, though, the concept that's super important is the completely specified wave function is still only giving probabilities of finding a particle. And what this means is that quantum is fundamentally probabilistic. This is the origin of the idea that things like, for example, radioactive decay are fundamentally probabilistic, but this is making a stronger statement. This is making the statement that reality itself is fundamentally probabilistic. It's not that we don't know where the particle is, and then we have a probability of finding it. It's that it literally is no place with any certainty, okay? This is about the only thing there is to know about the system is the wave function, and the wave function only gives, when squared, the probability of finding the particle at position x. And so that's it. The wave function can be used to find other things, but what it's not going to do is tell you exactly where a particle is. And more importantly, there is no truth of the matter as to where the particle actually is. If the wave function is describing an electron, there is no electron independent of the wave function that exists, that is somewhere. The wave function exists and will tell you things about what you'll measure when you sort of measure properties, including giving the probability of finding an electron somewhere. But it's not that the electron is secretly there and we just don't know. The state of the system is completely specified by the wave function. And that's a pretty radical idea, and one we're going to have to unpack moving forward.